So I'm a bit sleepy this morning because I was on BBC Radio this morning. And I was all prepared to give a very careful explanation of what it means to use gravitational waves to probe the Big Bang and all that. And then I came on the radio and the guy said, "So tell me about this bet." How did you come to make the bet? How much is it for? You know, and that's the entire interview. It's all about that. So people are much more interested in betting. It was the BBC economics correspondent, so. Anyway, I'm halfway to winning my bet. But because of that, all this excitement about gravitational waves, I thought I would tell you a bit about gravitational waves. So this is a change in the usual course. And it's tremendously exciting that gravitational waves propagate through space. They're a form of radiation, like electromagnetic radiation. But they have some advantages. For example, the gravitational waves go straight through the plasma of the early universe. It's completely transparent to them. So if you detect gravitational waves, you can just look right through the plasma to time zero and literally see the beginning of the universe. So that is why there's all this excitement about detecting gravitational waves. And all the different theories of the beginning of the universe are under scrutiny now, experimentally, which is very exciting. So let me just basically give you a picture. You probably heard about this BICEP experiment. It sits on the South Pole, BICEP 2, and it measures radiation coming from the very early universe. Of course, it's going through our galaxy, well, the atmosphere, our galaxy, a bunch of other galaxies on the way. And so there are lots of interference with the signal from the early universe, but basically they're looking at the surface of the hot plasma. This hot plasma is 400,000 light years away from the singularity, and this distance is 14 billion light years. Okay, so we're seeing almost all the way back to the singularity itself when we measure the microwave background. Now, BICEP 2 doesn't measure gravitational waves, it measures microwaves, but basically they can make a picture of the surface of the plasma. And what happens is that if there are gravitational waves produced at the singularity, they will travel through space, and they squeeze space in one direction. If they're traveling in this direction, they're transverse. We're going to see that in a moment. They're transverse, like electromagnetic waves. So whereas electromagnetic waves have an electric field going up and down and a magnetic field going the other way, gravitational waves, if they're traveling along, squeeze space in one transverse direction and stretch it in the orthogonal direction. And there are two independent polarizations, as we will see. And so basically, if there were gravitational waves emitted from the singularity, it would be squeezing and stretching this plasma of the early universe. And that squeezing and stretching creates polarization of the light emitted from that plasma. Okay? And the reason for that is that if you have an electron on this plasma, what causes it to emit microwaves, which we will then see, is that it's jiggled up and down. Okay? And if it's jiggled vertically, it's going to emit the electric field it creates is going to change in the vertical direction. So it creates a polarized electric field in the direction of the jiggling. And the perpendicular to that, there's a magnetic field. So if you look at the surface of the plasma, okay, and if you squeeze the plasma in one direction, that's what the gravitational waves were doing. So imagine the wave is coming straight out of the plasma. Usually they're at some angle. imagine it's coming straight out of the plasma, squeezes the plasma in one direction, stretches it in the other direction. So the light being emitted from the plasma over here, incident on this electron, which is going to scatter it to us, is blue shifted because the plasma is just moving towards it, right? So it's blue shifted, comes out here, so this motion, this wave traveled, this is an electromagnetic wave, travels down and then scatters. Now you ask, what are the possible polarizations of that wave? Well, as it's traveling down, the electric field's going this way, okay? Let's say, for example. When it scatters, it cannot scatter into our direction because that would be a longitudinal wave. Okay, so the only waves which scatter are the ones, if we look in polarization this way, the sources of them come from the sides. Okay, so basically a polarization of this type is going to see this stretching of the plasma, and so it's going to be redshifted. So this polarization will be redder, this polarization will be bluer, okay, and you will see a net polarization caused by the gravitational wave. So it's just an indirect effect in several respects. You don't see the wave's got to push the plasma around, the plasma's got to scatter light, then you see the polarization. So that's what they're looking for, is polarization, and as you know, in March, they claimed they'd seen it, the signal of the Big Bang, and all the inflation advocates were cock-a-hoop, and everyone talked about Nobel Prizes. But there were serious problems with the experiment, evident from the start, and so I was critical right from the beginning. Besides which, inflation's really not a very good theory at all. It's nothing like Einstein's theory, okay? Inflation, you have an arbitrary function which you fit to an arbitrary, you measure one function, you fit it to an arbitrary function. Well done. It's a very adjustable theory, and it's not in the same category as the theories that I'm telling you about. So I've always been skeptical about it, but nevertheless, other people are more enthusiastic. So, so on Sunday they got their comeuppance, and the signal went away. It still might emerge again, because all that's really been shown is that the dust in our galaxy emits polarization at more or less precisely the level that BICEP measured it, okay? So that's quite a coincidence. If it's, you've seen something, we know dust exists, and it emits at exactly the level you saw. Well, it could still be partly gravitational waves, and so they're hoping that maybe not everything they saw is dust, but that's a very long shot. And in November, Planck and BICEP 2 are going to cross-correlate, and that will be the best way of sort of removing the dust, trying to see if there are any gravitational waves there. They seem to be optimistic. There will be some, but at the moment there is zero evidence, so I am very skeptical. Yeah.
There's absolutely no chance for the RRE to be as large as they claimed it to be initially.
No, that's already ruled out.
So that's ruled
In fact, it was already ruled out when they claimed it. Okay?
Okay.
People are remarkably uncritical, and it's very important for you as young scientists entering this field to realize that the field of the theoretical physics engages in a lot of groupthink. Okay? There are bandwagons, and they run off in some direction, and eventually the wheels fall off. And it's very important to keep a skeptical mind and to be aware that not everything everyone tells you is the truth. They're doing their best, but people like to believe strange stories.
Another question.
Yeah.
So so the dust polarization is happening at the same frequency that BICEP is measuring.
Yes.
It's just the one. So
No, the polarization is at all frequencies.
yeah, I know.
Right.
But BICEP isn't sensitive to, like, they did the.
Well, this was the big problem in their
Yeah.
experiment. That's why I was so skeptical when it
Right.
first came out, because the problem is you know there's dust, you know there's radiation from electrons. The only way to distinguish it from gravitational wave signal is the gravitational wave signal would, of course, be frequency independent.
Exactly.
Everything gets stretched and squeezed the same way, so in all frequencies you'd see exactly the same effect. The dust is totally different in all frequencies.
Yeah.
So dust emits much more strongly in high frequencies. So the only way to separate the gravitational wave signal from the dust signal would be have several frequencies and use the higher frequencies to measure the dust and then try to subtract it, or at least estimate it, from the channel that you're using to see the gravitational waves. So BICEP only had one frequency. And one frequency is good if you're trying to set an upper limit. If you see nothing, that's great. And they expected to see nothing. Okay? So they thought, let's put all of our eggs in one basket. We'll try and set an upper limit. And then they saw something. And then they kind of forgot about the limitations of their experiment. And they got overexcited and claimed they had measured something. It was unwise. Yeah.
Did you say the polarization is measured indirectly through like the redshift and blue shift?
Yes.
Why couldn't they?
No, I'm sorry. The polarization you're measuring is the polarization of the microwaves.
Right.
Okay, it's nothing to do with the gravitational waves. It's only indirect in that sense. That the source of all of this is gravitational waves, but it pushes the plasma about, the plasma creates the light, and then the light is polarized. Yeah. It's only indirect in that sense. Okay, so let's talk about gravitational waves. And before we do that, I'm going to talk about general property of gauge theories. General relativity is a gauge theory. And so I'm going to solutions of gauge theory. So I'll just remind you what a gauge theory is. And gauge fixing. So as in everything, Maxwell is the origin of all truth. Okay, theoretical physics said, let there be Maxwell. And so let's start with Maxwell. So Maxwell, we have our equations in empty space, or with no, sorry, we'll leave it current. So Maxwell's equations with some source. And if you remember, let me write it this way, F mu nu is d mu a nu minus d nu a mu. Now, you'll remember that this theory is gauge invariant in the sense that if I replace a mu with a mu prime, which is a mu plus the derivative of some function where epsilon of x is arbitrary, then d mu f prime mu nu is still equal to j nu. So this was the first example of gauge invariance discovered, that the vector potential, a mu, is not a physical thing. It's not determined by the theory. It's undetermined. It's only determined up to gradients. So if you try to solve Maxwell, obviously you're not going to be able to, because the equation, if you have a solution of this equation for a mu, well, this is also a solution. Okay, so there's clearly not going to be a unique solution of the equation. Now, it's a linear equation, this one, so we can Fourier transform. Let's write it all out. So I'm going to So remember that a d mu with a raised index is just eta mu nu d nu. And then d mu a mu minus d mu a mu equals j nu. So I have to solve that equation. Now, it's only linear, so we can Fourier transform. Okay, so it's linear. So we're going to set a mu equals to a sum over k, a mu tilde of k e to the I k dot x. Okay, and this means k mu x nu eta mu nu.
Should the nu on the j be down? Or?
Yes, it could be down. Yeah, it should be down because it should match. So this is the this a mu tilde will be the Fourier transform, and similarly for j. For j nu. So if I substitute that into the equation, what I get, when I have derivative with respect to x, I get I k mu. And so this equation becomes minus k squared delta mu nu plus k mu k nu times a twiddle mu equals j twiddle mu. I think I've kept the index up here. Get the index up. Okay, and so this is how you solve the equation through Fourier transform. Now it's just algebraic. There's no differential equation to solve. But you immediately notice a problem. This is a matrix M mu nu. And so it follows that A twiddle mu is the inverse matrix times mu nu of J nu. But is there an inverse? Can I invert that matrix? Well, one way to check is to, if a matrix is invertible, all of its eigenvalues must be non-zero. Conversely, if this has a zero eigenvalue, it's not invertible. Does this matrix have a zero eigenvector, a vector whose eigenvalue is zero? Okay, you can see it by inspection. You should be able to see it by inspection. There's only one vector in the game, k. Okay, so the problem is this doesn't exist because m nu mu k mu equals 0, right? Because if I multiply with k mu, this term is going to be k nu with a minus k squared. This will be k nu with a plus k squared. So k mu is a 0 eigenvector. Is an eigenvector with eigenvalue 0. So it follows that M mu nu has one of its eigenvalues is 0, and that means it's not invertible. And that means you cannot solve. There's no unique solution to the equation. So these two things are the same. You see the gauge transformation just means when I Fourier transform the gradient of epsilon, I'm going to get k mu times some function of k. And And so I'm going to be shifting A by K. And if I shift by A by K, it's still a solution of this equation. Okay, so this is a general problem with gauge theories, that their equations of motion do not have unique solutions. Yeah. Sorry?
Can you guarantee then that there is a solution?
Yes, there is a solution, but it's not unique. There is a solution up to translations by K.
How can we see that though? Like, if I was just talking about this in terms of matrices,
We'll see that in a second.
Okay.
You guarantee there is a solution by fixing a gauge.
Okay.
Okay? And so that's what you need to do. So another way of saying it is this is not really 4 equations for 4 unknowns. It's really only 3 equations for 4 unknowns. Okay? And the only way to fix the solution is to arbitrarily pick one of the components of A, or some linear combination of them, and then you will have a unique solution. So, to find solutions, we need to pick a gauge. One example is called Lorentz gauge. And so the first thing to do is to show that given an A mu, you can always pick this gauge. Okay, that's rather easy to show. So given an A mu, consider A mu prime, which is A mu plus D mu epsilon. And we're just going to choose this epsilon in order to enforce that condition on A mu prime. Okay, so D mu A mu prime is equal to D mu A mu. And by assumption, this was not 0. Okay, this is some arbitrary solution, plus D mu epsilon. And we can set this equals 0 if d squared epsilon equals minus d mu a mu. And this is the wave equation for which the d mu a mu term acts as a source, and that can always be solved. Okay, one way to see that is to Fourier transform it. It can always be solved. For epsilon, because if we Fourier transform this, I get minus k squared epsilon twiddle equals minus d mu a mu, well, minus, yeah, let's just write it as d mu a mu twiddled, the Fourier transform of the source, and then I can divide by k squared. So epsilon twiddle equals d mu a mu twiddle over k squared. And then I can Fourier transform back to get epsilon. So this is called Lorentz gauge. Okay, and there are many other gauge choices possible. You can pick A naught equals 0. This is called temporal gauge. Or div A equals 0. That's called a Coulomb gauge. Etc. So there are all these possible gauges you can choose, and you try and choose a gauge. Well, when you choose a gauge, you should ensure that for the problem you're considering that gauge always exists. And that is sometimes not clear or not true. So you need to pick a gauge that exists, that And once you've chosen the gauge, then the Maxwell's equation have a unique solution. Yeah.
What is the process by which we can see that a gauge exists in our problem?
It actually depends on the physical situation. Okay. So the only general statement I know is that every gauge has problems in some situations. Okay. So I'll tell you, yeah, I don't want to get too far diverted, but the question of choosing gauges is rather subtle. Let me just say that. So, for example, if I try to pick Lorentz gauge in electromagnetism, and I choose it in a situation where I have a charged shell moving out at the speed of light, Lorentz gauge becomes singular. Okay, because Lorentz gauge sort of signals propagate at the speed of light. One has to do the calculation to see it. But there are sort of physical or nearly physical problems where every gauge has problems. So for every gauge, if you look hard enough, you can find a physical problem where that gauge is a bad gauge. And so what you have to do is always pick the gauge which is a good gauge for the situation you're interested in. And many gauges are good in many situations, but one always has to be aware that gauges can go singular. You see, it's sort of obvious, because imagine I had a good gauge, all right? And then I do a gauge transformation, but epsilon is a singular function. Well, then I'm in some new gauge, but now everything's going to be singular. Whereas if I'd started in that singular gauge, I would say, oh dear, the whole problem is a disaster, everything's singular. And so what it's telling you is, no, you started in the wrong place. You need to start in a gauge that's not singular. Okay, so this is just the way physics works, is that any specific, you see, in GR is related to the choice of coordinates. For any particular space-time geometry, an infinite number of choices of coordinates. If you happen to pick some bad coordinates, you're going to find singularities. But don't blame the theory, okay? Just because you picked the bad coordinates. So you have to go back to the beginning and pick some coordinates in which there isn't a problem. Right, so it's all rather slippery. And again, it's this problem that we don't know how to describe nature on her own terms. The only language we have is numbers. When we translate geometry or gauge theories into numbers, there's all this redundancy. This is redundancy, okay? The a mu variable are redundant, because if I shift them by a gauge transformation, they're still perfectly good variables. Coordinates are redundant. All the different coordinate systems, just a redundancy of our description. You can use any number of coordinate systems, and they're all describing the same thing. Yeah?
So you showed that it's not like one-to-one, this M guy?
Yes,
which means
it has
you
a
don't have
kernel.
uniqueness? Yeah, exactly. Yes. But is it, I guess maybe, is it a map of the same spaces here? I was going to ask, are you guaranteed existence? Like, is it onto?
Yes, I've assumed all kinds of things. One of the things I've assumed is that there is a good Fourier transform, right? And I've assumed the functions are smooth. I've assumed the functions are smooth, so I can differentiate them. So I've made all the sort of normal mathematical assumptions that we make in physics, which is that things are smooth and we can differentiate them and so on.
Yeah.
Given all that, yes, it's you know, if the Fourier transform exists, then we're just down to linear algebra, right? Literally, at each momentum k, we just have linear algebra to do. So we have some matrix, and we have to invert it. And so, you know, one can find the inverse. In fact, that's called, when you get to do QED, you'll just write down the full set of solutions of this equation with a parameter psi, and the parameter is the gauge parameter. Okay, so I can write the general solution to this, which involves an arbitrary constant psi, which is precisely related to this zero eigenvector. I can try and do it if you want, but I don't want to get diverted into it. Okay, so this gauge invariance was already there in Maxwell, and the one just has to be aware of it. Now let's do general relativity. Oh, by the way, let me just do some simple counting. Okay, so it looks like A mu, so naively, we would say A mu has 4 degrees of freedom. Because they're 4 functions of space-time. But in fact, we only have 3 equations. You see, we have this equation, d mu f mu nu equals j nu. This is really only 3 equations. Okay, why is it only 3 equations? Because it looks like it's 4 equations, because nu goes 0, 1, 2, 3. But the problem is this obeys an identity. But d nu, d mu, f mu nu equals d nu j nu equals 0. This is an identity. So our 4 equations obey one identity. So there are really only 3 equations. Okay, so I've got 3 equations for 4 unknowns. So obviously I'm only going to be able to determine 3 of these 4 functions. Okay, so my number of degrees of freedom went down to 3. But it's actually worse than that, because not only did it go down to 3, but the whole theory is invariant under gauge transformations. Okay, so but we have invariance a mu prime plus d mu a mu, d mu epsilon, a mu prime equals a mu plus d mu epsilon is also a solution. And so this tells me that I can reduce the degrees of freedom by 1 more. DOF goes down to 2. Okay, so when you have a gauge theory, you actually lose 2 degrees of freedom. You lose 1 because of this identity. Whatever a mu you find, okay, it has to satisfy this identity. And so that identity, which is also called the Gauss law constraint, takes you down to 3, and then you still have some invariance, gauge invariance, and that takes you down to 2. So in GR, this is the same way. So, and these 2 are really the 2 perpendicular polarizations of electromagnetic waves. Okay, is that this is the reason why there really aren't 4 electromagnetic waves. There are 2. This condition is transversality. It tells you the wave is transverse to the k vector, and this transformation tells you that the a naught component, the time component, can always be gauged away. So electromagnetic waves really only have two independent polarizations, and it will turn out gravitational waves are the same. In spite of the fact that we have 10 components of the metric tensor, when we take into account the Bianchi identities, which are the analogous analog of these, that goes down to 6. And when we take into account general coordinate invariant, it's another 4. It takes us down to 2. And there are only 2 independent degrees of freedom in the solutions of the Einstein equations. So let's just write down the Einstein equations. G mu nu is 8 pi g t mu nu. This looks like 10 equations. Okay, but we have the Bianchi identity. D mu G mu nu equals 0, which any solution has to satisfy. And so these are 10 equations. This is 4 equations. So whatever G mu nu I find, it has to satisfy 4 equations. So there really were only 6 free solutions available. And we have 4 general coordinate transformations. X mu goes to x mu prime of x. And so these together take us from 10 minus 4 equals 2 free functions in the solutions. And these are the 2 linearly independent polarizations in gravitational waves. Okay, so we're going to see this in detail when we actually solve the equations. It sounds a little abstract at the moment. So under general coordinate transformations, and I think you did this in class, x mu goes to x prime mu, g mu nu goes to g mu nu of x, goes to g prime mu nu of x prime, which is dx dx prime dx dx prime Okay, so the change, that's the change in the metric. And it's worth just staring at this equation a moment. You see, when you change coordinates to g prime, you're now in the x prime coordinates. And the g prime is a new function of x prime. Okay, you had some g, which is a function of x, a given function of x, like x squared or sine x or something. Now I've got my new g, g prime. It's a different function of x prime. The change in the function is called the Lie derivative. Okay, it's a fancy name, but all it means is that when you change coordinates, you change the function. So the metric in spherical polar coordinates, will be a 4x4 matrix with sine squared theta. The metric for a sphere, for a two-sphere, with a metric in stereographic coordinates will have other functional dependence. And so what we're really interested in, the functional, let me say it a different way. If g mu nu of x is a solution of the Einstein equations, then g prime mu nu of x is also. Okay, so I take my g prime, which is a different function of x prime than g was of x. Take the g prime, just replace its argument with x. Because in the Einstein equations, x is just a sort of dummy variable. I mean, there's d by dx's, and there's functions of x's. But you can replace x prime with x. just by relabeling. And what that means, so this is just relabel. Just don't change anything. Just call x prime x. Okay, so it follows that if you've got this solution g prime of x prime, I can just call x prime x. And so g prime of x is also a solution of the Einstein equations. So that tells you you can use this coordinate freedom to change the function. And so let's calculate that change. Let's do an infinitesimal coordinate transformation that x prime mu is x mu plus epsilon mu of x. So an infinitesimal coordinate transformation. That just means epsilon is small. Epsilon mu is much less than 1. So if we do an infinitesimal coordinate transformation, then of course it follows that x mu is x prime mu minus epsilon mu of x prime. Okay, and I drop terms of order epsilon squared, so I'm allowed to shift the argument of epsilon from x to x prime because they're equal to first order. Okay, so x mu is equal to this, to first order in epsilon. And now I can plug this expression into there and work out g prime of x prime. So from star, which is this equation, we get g prime mu nu of x prime given by this formula. But actually, what I want is g prime mu nu of x. I want the functional dependence of the new metric on its argument. And this is going to be equal to g prime mu nu of x prime minus from, sorry, it should be g prime x prime minus g. Okay, let me just think about this. Yes, so use this formula. This is g prime mu nu of x prime minus, just using that formula here, minus epsilon lambda g prime mu nu of x prime. Okay, because x is x prime minus epsilon. Sorry, this is a derivative. But this term is already of order epsilon. So here I can replace both g prime and x prime with the unprimed coordinates. So this will be g prime mu nu of x prime minus epsilon lambda g mu nu comma lambda, right, to first order in epsilon. Let's move the middle one up. And the g prime of x prime I can compute from here. So what I end up getting is that delta g mu nu of x, which is g prime mu nu of x minus g mu nu of x. Okay, that's the definition of delta. It means that the change in the functional form of the metric after this coordinate transformation. And that's equal to, from here, I get two terms, minus epsilon alpha, comma mu, comma nu g mu alpha, minus epsilon alpha, comma, mu, g, mu alpha. No, I've written that out. G nu, G alpha nu. And then minus this term, epsilon lambda, G mu nu, comma, lambda. Okay, so this is the functional change in G mu nu induced by a coordinate transformation. And it's also known as the Lie derivative. So that's the change in the metric. Was this clear? So the way that I calculated g prime of x prime was just to use this formula, and then dx prime is going to give me, right, dx mu dx prime nu is going to give me delta mu nu from this formula minus epsilon mu comma nu to first order. And since I have the expression of first order, I can then replace x prime with x, because x prime equals x up to first order. And that's how I got these terms, just differentiating x with respect to x prime, and then setting x prime equals x in the argument. Okay? So there's a nicer way of writing this. Makes it look more covariant. Yeah, I'll bring the top one down. Or, you probably can't see that one. A bit more. Or delta G mu nu is equal to minus epsilon mu semicolon nu minus epsilon nu semicolon mu. Okay, so when you work out those semicolons, that means use the covariant derivative. It means use the Christoffel, the Christoffel symbol or the connection that I given you before. And when you use the connection, you're going to get this term. Okay, so this term is going to come from those connections. So I'll just leave that as an exercise to work it out. But this is the expression that's often used for the Lie derivative. So when we solve the Einstein equations, we need to pick a gauge. When we solve the Einstein equations, we need to pick a gauge that's completely equivalent to saying we need to pick coordinates. And the analog of the gauge freedom in electromagnetism under A goes to A mu plus the gradient of a function is exactly this equation, that the change in the metric is the gradient of a 4-vector, epsilon mu. And epsilon mu is precisely the change in the coordinates. There is a big difference, which is that this is a linear theory. Okay, Maxwell's theory is linear. you know, the universe has been kind to us, and it gave us the linear theory to work with first so that we could understand it, because if it threw the nonlinear theory at us straight away, we wouldn't have a chance. Okay, but the nonlinear theory becomes linear if you make small coordinate transformations. At least the gauge invariance is linear, but only for small epsilon. You see, in this case, I didn't have to choose epsilon small here. Epsilon could be arbitrary, and this is all true. In this calculation, I've dropped all the epsilon squared terms. Okay, so Einstein's theory is a nonlinear gauge theory, and it's invariant under nonlinear gauge transformations. Nevertheless, you can understand a lot of this by thinking about the linear theory. And in the general case, we've got to pick a gauge. We've got to pick coordinates. So one choice of coordinates. Now, I want you to guess this. Okay, I've got to pick some coordinates. I've got 4 arbitrary functions, right? And I've got to write something down which is not gauge invariant, and I'm going to set it 0. Just like here, when I was trying to pick a gauge, what did I do? I wrote down this. This is not gauge invariant. And I said, this is 0, and that's a gauge, right? So I'm going to choose, whatever mu is, I'm going to choose my epsilon to ensure this is true. Or I wrote down a naught equals 0, also not gauge invariant, or div A equals 0. Okay, so choose something which is natural in the theory, and set it 0 by choosing coordinates. And that's how you pick coordinates. So what do you know of in this theory, which is not coordinate invariant? Metric. The metric is coordinate covariant. Well, you could try and set g mu equals 0.
No.
That would not be very good. You could also, you know, try this.
Covariant, I mean, the...
It's not very...
Connection. You can
Connection.
set the flat divergence of the metric to 0.
Say again?
You set the flat divergence of the metric to 0.
What do you mean by the flat?
In the sense that you contract one index with the partial derivative.
Of, oh, I see, like this?
Not the covariant.
Covariant would be bad, right? So you could do this. Yeah, that's a good idea. Yeah, that's a perfectly good gauge, at least as far as I know. It is a gauge. It's 4 conditions. It will fix 4 coordinates. There is a equals 0. Yeah, that's a reasonable choice of gauge. Let's just don't have any problem with that. There's another choice, okay? No, there is. Let's pick something else. What's not coordinate invariant? What could... We introduced something that was definitely not coordinate invariant, or even covariant.
The Christoffel symbols?
Yes, the Christoffel symbols, okay? So the only problem is there are too many of them, okay? Because it's symmetric here, it's a large number of things. We can't set all of them 0. But what we can do is just contract it with a metric. Okay, so that is a very nice gauge, and this is called harmonic gauge. And the reason it's called harmonic gauge is that if I work out, if I have a scalar phi, then box phi, and by box I mean the 4-dimensional covariant version of box. Okay, so it means 2 derivatives contracted. And this can be written as, this of course can be written as g mu nu d mu ordinary derivative of phi, because covariant on scalars doesn't have a connection. And so this is equal to g mu nu d mu d nu phi, and then minus gamma mu nu lambda d lambda phi, also contracted with the g mu nu. And then, of course, in this gauge, this second term vanishes because it's g mu nu gamma. So actually, this is equal to g mu nu d nu phi in harmonic gauge. And so, in particular, if we choose phi equal to x mu, okay, so just think carefully what that means. It's a bit of a strange equation, but we're deliberately picking things that are not coordinate invariant, okay? So by this I mean that this, I'm going to think of the time as a scalar function on space-time. Okay, so surfaces of t equals constant are level sets of some function, which is t. Okay, then box x mu equals g mu nu d nu x, better relabel these, alpha beta d alpha d beta x mu equals 0, right? Because two derivatives on x, on the coordinate, is 0. So this is the statement of a harmonic gauge. So harmonic gauge is equivalent to the statement that the scalar box, right, the scalar covariant box on the coordinates is 0. Kind of a nice way, and that's a harmonic. It's saying the coordinates are harmonic functions. Harmonic means that box, they're eigenvalues of box. And in this case, this eigenvalue is 0. So that's a very nice coordinate system. And the Russian physicist Fock, who invented Fock space, wrote a beautiful book on GR in the 1930s, I believe, or 40s, where actually what he claimed is that the only coordinate system that made any sense in GR was this one. Okay, so he was a very powerful mathematical physicist, but I think on this point he was confused. But nevertheless, it shows you there are many nice properties of this coordinate system. And in fact, you might be aware that until about 4 or 5 years ago, maybe it was longer, until about 2005, it was impossible to solve the Einstein equations on a computer. They're just too difficult. 10 equations, nonlinear. Nobody could get the codes to work. And the breakthrough in solving the Einstein equations on a computer was to use this gauge. Okay. There's a little bit more to it than that, but that was the ingredient. So many people studying GR thought this is rather an old-fashioned gauge. They were picking more geometrical gauges and so on. And then ultimately, this gauge proved to be the one in which the numerics were better defined, more stable. Okay, so that's been a long preamble. We're now going to get into gravitational waves. Let me just mention some other coordinate system. Another common choice of coordinate system is G0 mu equals 0. G0 mu equals delta 0 mu. And by that, it means you choose G0 naught, there must be a minus sign there. You pick G0 naught equal to -1, and you pick G0 I, the space, the coordinates with one space index and one time index, to be 0. This is called synchronous gauge. And that's also very useful coordinate system. But that one goes singular, generically goes singular rather quickly. And what it represents is you think of space and time, where I pick some surface in space-time, and I call it t equals 0. You can pick any three-dimensional surface, which is space-like. You can pick to be time 0. Okay, and then you're going to foliate space-time with some choice of time slices. Okay, so each time slice is three-dimensional. And the choice of synchronous means that I think of a bunch of particles on this time slice, and I let them go, free-falling in the space-time, and I choose them to have 0 velocity with respect to the initial slice. So they're actually going at right angles with respect to the initial slice through space-time. And then the time they measure on clocks is given by the time coordinates. So the space coordinates are the location of these little clocks. So at every point in space-time, I can tell you which clock hit it. And its space coordinate is the coordinate of the clock on the initial hypersurface. And the time coordinate is the time shown by the clock. So it's a very physical set of coordinates, very nice set of coordinates. Anyone tell me a problem this coordinate system might have? Okay, so imagine doing this, and you set up these particles, you let them go. Any problems that might obviously... Yeah, very good. Okay, so with this guy, and they meet, and whoops, this space-time point has 2 coordinates. And that's a sign that it's singular. So synchronous coordinates generally go singular fairly quickly. So now let's get on to gravitational waves. But I hope I've made you feel a little bit nervous about coordinate transformations. Because when we come to black holes and Schwarzschild coordinates, you'll need to be nervous. Okay? Because you'll need to realize that we just picked some coordinates without any real thought. And if we find singularities, like the metric was singular on the horizon, you know, is it the fault of the coordinates, or is it really a problem with the theory? And of course, what we'll see is it's just a problem with the coordinates, and we need to pick some better coordinates. Okay, so gravitational waves. So this involves rather a lot of algebra. So I'm just going to give you the main equations, and in view of time, I'm going to, I'll try and give you the main ideas, but near the end, I'm just going to have to quote a formula and refer you to somewhere where it's all worked out. So let's take the weak field, weak gravitational field. And by that, we just mean that G mu nu is the Minkowski metric plus H mu nu. And H mu nu is small. The magnitude of H mu nu is small. And so we just work to first order in H mu nu. And then we can just do the calculation. This is boring, but I've given you all the formulae you need. So this is d squared h mu nu. I'll call it box, actually. Box I'm going to define as eta mu nu d mu d nu. Okay, if we're working to first order in metric perturbations, we can ignore all the h's coming from covariant derivatives. And so this box here is the flat space box. And so this is what you get. H nu, lambda nu, comma mu lambda minus h lambda mu, comma nu lambda plus h lambda lambda, comma mu nu. Okay, so this is easy to get this formula from the formula I gave you before, where you had the Riemann tensor as being derivatives of the metric, etc. Well, it was things like this. So it went as second derivatives of the metric plus gamma gamma terms, and then just substitute in for g equal to h, and this is what you'll get. Now, this term is nice, right? That's telling you that the Einstein equations are going to be box h equals t mu nu, something like t mu nu. These terms are kind of messy, but you can reorganize them. You can write them as minus h lambda nu comma lambda minus 1/2 h lambda lambda comma nu all comma mu, and then the same thing with mu and nu interchanged. H lambda mu comma lambda minus 1/2 h lambda lambda comma mu all comma nu. And it turns out that in harmonic gauge, which is g mu nu gamma mu nu lambda equals 0, well, if I work that out to first order in h, this just implies that h lambda nu comma lambda minus 1/2 h lambda lambda comma nu equals 0. So in harmonic gauge, these extra terms both vanish. Okay, and so r mu nu is minus 1/2 box h mu nu to first order in harmonic gauge. So that's a nice result, and it's a good reason to use harmonic gauge to study gravitational radiation. And in empty space, in the absence of matter, well, let's say in the vacuum, I shouldn't say it's in the vacuum because the vacuum has dark energy, and we know that. But in flat space, let's say, we don't live in flat space, but in flat space, I don't mean flat space either, because then the Riemann would be 0. If t mu nu equals 0, t mu nu equals 0, the Einstein equations allow waves propagating at the speed of light. Okay, so just like Maxwell, you could get very excited and say the first prediction of this theory is there should be wave-like solutions. Only Maxwell got there first, so I guess you can't get that excited. Now, naively, you might say there are 10 waves, right? Because h mu nu has 10 components. It's a symmetric 4x4 matrix. But as I've already discussed, when we think carefully about this gauge freedom, we're going to discover that 8 of those 10 solutions are fictitious and either don't exist or can be removed by gauge transformation. Notice that, okay, so consider solutions. Of the form h mu nu equals sum over k, epsilon mu nu of k. K is this 4 vector, e to the I k dot x, plus complex conjugate. Okay, so epsilon mu and when I write sum over k, by that I could mean a continuous integral over k. Could be integral d4k. It's just a formal notation for summing over the all values of k. Of course, if that's a solution, you must have r mu nu equals 0 implies that k squared is 0. So when I sum over k's, I've got to make the k naught, k0 squared is k spatial squared. So this sum really reduces just to a sum over spatial k vectors, and the k naught is equal to modulus of k. Uh-huh.
So I'm just a bit confused here. You've written down like this equation for r mu nu.
Yes. Here?
Yep, up there. And then you said that we set t mu nu to 0.
Right.
Now the Einstein equations are looking at the Einstein tensor, not...
But remember that I told you that the Einstein equation, so that's the Einstein equation.
Yep.
So this equation reads r mu nu minus 1/2 g mu nu r equals 0.
Yep.
Now I can contract it with a g, and I get r minus 2r equals 0. So this equation implies r equals 0.
Right, okay.
And then this equation implies r mu nu equals 0.
Thank you.
Okay. So the Einstein equations without matter really just read r mu nu equals 0. And to first order in H, that's just box h mu equals 0. And the box is the flat space box. And so the solutions all have k squared equals 0. And then I'm going to pick the positive energy solutions. K naught is actually the energy of the solutions, and I'll pick positive energy solutions. Okay, so now where am I? Right. We also have to have the harmonic gauge condition. Harmonic gauge condition we wrote down up there, and what it reads is that k mu epsilon mu nu minus 1/2 k nu epsilon mu mu equals 0. So we've got this 4 vector, k mu, but the epsilon tensor has to be transverse or satisfy this condition with respect to that for the 4 vector specifying the propagation of the wave. We still have gauge freedom. Why? Because this harmonic gauge condition does not uniquely specify the coordinates. So if I remember a coordinate transformation, under a coordinate transformation, the metric changes by this form. Now let's see, we should be able to read that off the Lie derivative. It's in that middle board. So this is how the metric changed. So these, if I consider the transformation of h, okay, I've got some metric which is eta plus h. The transformation of h will be given by this term, where I replace g with eta, and I treat epsilon as of order h, and this term as well. Now in this term, the g is eta plus h. So this term is of order h, okay? But if h is of order epsilon, if epsilon is of order h, this is higher order in epsilon and h, so I neglect that term. We treat epsilon as of order h. And so what this means is that, so this still satisfies harmonic gauge. H prime lambda nu comma lambda minus 1/2 h lambda lambda comma nu equals 0. Let's just see that. You see, if I've got some h satisfying that condition, and I plug in this h prime, I'm going to have two extra terms. The extra term here will be minus epsilon lambda comma nu lambda, and minus epsilon nu comma lambda lambda. That should be from the first term. Okay. Yeah, I haven't used ideal notation because this epsilon is different than that epsilon. Okay, so don't get confused by, this has two indices. This epsilon only has one index. Okay, it's a coordinate transformation. So this is my equation for the h prime. The h prime got shifted by these two epsilons, and then I have plus 1/2. Now here I have the h lambda lambda shifted by epsilon lambda lambda with a factor of 2, because there are two terms over there. And this is all comma nu. And now if there's any justice in the world, this should be 0. Sorry, it's not 0. This is equal to minus box epsilon nu, right? Because this term cancelled this term. And what I've left with is box epsilon nu. But box is just k squared. And k squared was 0. Okay, so satisfies this if epsilon, if box epsilon equals 0. So epsilon nu equals 0. Okay, so what that means is that we're free to change the solution from h to h prime And the effect of that transformation so we can change so by a coordinate transformation we can change epsilon mu nu goes to epsilon prime mu nu, which is our original epsilon mu nu, plus k mu epsilon. I should have really called this C. I'll leave it like epsilon anyway. Plus k nu epsilon mu, okay, where these are all twiddles. Epsilon mu of x equals sum over k squared equals 0 of epsilon mu twiddle of k e to the I k dot x. Okay, so some words. This guy epsilon of k is called the polarization vector, polarization tensor. Polarization tensor. Okay. The general solution of the wave equation for h mu nu looks of this form, but then we just argued that you can, is of this form where epsilon satisfies this harmonic gauge condition. But I'm still free to do a coordinate transformation with the coordinate transformation being epsilon mu. As long as epsilon nu is harmonic, box epsilon nu is 0, and so epsilon can be written this way. And then the consequence of this coordinate transformation is to change my polarization tensor by terms involving k and epsilon, with epsilon tilde mu being an arbitrary function of k. Arbitrary function of k. Okay, so we tried to solve the Einstein equations. At first sight, it looked like there were 10 free functions. We had these harmonic gauge conditions, which reduced them to 6. And then we found that even when we've picked a gauge, harmonic gauge, there's still a residual gauge freedom, which is 4 more free functions. And using those 4 additional free functions, we can reduce the number of gravitational waves propagating to 2. So we will do that algebra next time, and we'll see that there's really 2 linearly independent polarizations for gravitational waves. And I'll also try and give you a quick derivation of the radiation from gravitational waves. So I think I've mentioned this before, but there's a famous binary pulsar. Maybe I'll show you this picture at the beginning next time. PSR 1913 plus 16. And this was measured by Hulse and Taylor. So you have 2 neutron stars, 2 compact objects, and they're orbiting each other at a very fast rate. I don't remember what the rate is. It's not 415 per year. but it's pretty fast. I did check that, by the way. It is 415 per century. This binary pulsar is in orbit. One of these guys is emitting pulses, which we measure. And as this thing is in orbit, it's also emitting gravitational waves. Okay? And so next time we're going to derive a formula called the Landau-Lifshitz formula for gravitational wave emission. And that will tell you how much energy per unit time this object sends off in gravitational waves. And because it's sending off energy, its energy is falling. And so it's becoming more negative. It's basically falling down the gravitational potential well, in which each star is trapped in the other's gravitational field. And so their combined energy is negative. And as it loses energy, it gets more and more negative. They get closer together. They go faster and faster. And what they observed is the pulse frequency coming from one of the satellites. They inferred the orbital period, and they see this orbital period getting shorter over time. And what they found is that they could, by measuring all the parameters of this system, they could predict exactly how much energy it should be losing per unit time and compare that to the predictions of Einstein's theory. And there were no free parameters in the fit. It's an absolute prediction. And it's spot on to within less than 1% now. So you can tell that this loss of gravitational waves is having exactly the effect predicted by general relativity. And I think they won the Nobel Prize in 1997 for that. And I have to tell you a funny story, because they were at Princeton, where I used to teach. And when they won the Nobel Prize, we had a little celebration, which was champagne in the quad. And so we're all standing there drinking our champagne. And one of the more mathematical physicists at Princeton came up to me and said, "What have they won this prize for? I don't really understand, because this is a classical effect, right?" We know what the result is. I mean, it's got to be right. Einstein's right. There's no doubt about that. How can you possibly give somebody a prize for confirming this classical effect? The only real problem is quantum gravity. Okay? It's not quantum at all. So it's very funny. Some people have a sort of warped perspective. This is, even though it took nearly a century to confirm this prediction of Einstein's theory, it's completely spectacular that it's true. It's just an absolute prediction, like I say, with no free parameters, like the perihelion shift of Mercury. It's just telling you this theory is right, way beyond any right. It has to be right. It's a total miracle that such a simple theory, conceptually simple, even though the algebra is a mess. The theory is incredibly conceptually simple, that gravity is just the bending of space and time. And this theory is right to ridiculous accuracy. OK, so we'll do a little bit more on this next time, and then we're going to fall into a black hole and discover that time goes backwards, time goes forwards. We'll be in a white hole and a black hole, and we'll be in a new universe, and we'll see all of our concepts being challenged. Any questions? You can erase anything. Yeah.
Just 1 second. One thing about that black hole.
Sorry.
Sorry. In the bottom right part, when we were deriving that equation, I can see that we are having the epsilons, first the vector epsilons,
yes,
and in the last part, the tensor epsilons. Does that make any sense, or
oh,
typo
okay.
there, or?
Well, it's just because I wrote it wrong, undoubtedly. I think the comma should be there probably. Let me see.
So one of them should be up though, shouldn't it?
No,
the
it's
last says.
flat, so it doesn't.
I think there's a comma here, no?
But still, one of them should be.
Comma new.
It's flat, so it doesn't matter.
So what I did is I just plugged this stuff in there, right? I just plugged this correction with the minus sign into this formula. That's how I got this line. So the second term, I take the h lambda lambda, which is minus 2 epsilon lambda comma lambda.
Okay.
With the, so yeah, I just forgot this comma, so thank you for that. This should be lambda comma lambda.
Okay, thank you.
Okay.
And also the one before, one of the lambdas should be up.
One of the lambdas should be up, you're right. Sorry, my only excuse is I was up late last night, but I do this anyway, so it's a feeble excuse. Okay, so from this point of view, slightly different. The conclusion is the same. The counting of modes was that we had 10. We had to pick 4 gauge conditions in order to solve the equations. So we picked those 4. And then we discovered those gauge conditions allow 4 free functions in the solution. So then I can adjust those 4 free functions to cancel another 4 components of the solution. So you end up with a conclusion that only 2 components of the h mu nu cannot be cancelled. Satisfy the Einstein equations and the gauge condition and cannot be removed by a gauge transformation. Those are the gravitational waves.
How can the gravitational waves carry energy if we have assumed T mu nu is 0?
That's a great question. Okay? That is a great question. So it works the following way. These equations are ridiculously powerful. Okay? So we say T mu nu is 0. There's no matter. How do I have any energy? I lost energy in gravitational waves. The answer is the following. That I think of G mu nu as a series in powers of h. Okay? So G mu nu will be, of course, for flat space, this is 0. Then it is G mu nu at first order. This is of order h. Then I have G mu nu at second order. And this is of order h squared. Okay, so now what I do is take my Einstein equation and put this in the left-hand side. Okay? So what I get is G mu nu at first order, right, is equal to this minus G mu nu at second order. Right? And this I call the energy in gravitational waves. By definition, is 1 over 8 pi g times minus G mu nu at second order. Okay? So if I ask, what is the effect of these second order stuff on the metric, it's exactly as if it was real stress energy. Okay? So basically, I've got these waves traveling along. They're going to deform the metric at infinity. They're going to deform the linear perturbation, which is how I'm going to measure the energy with the m over r. The second order gravitational waves are the carry the stress energy. It's completely ridiculous. But, okay. Now, then it gets a little worse because you say, is it really energy, or is it, is it geometry, or is it energy? They're all tangled up. And when you write this down, let me see, what is the way of saying it? Yes. So, what really matters, if something is energy, what really matters is that it's conserved. If it's not conserved, there's no point talking about it as energy. Okay? This metric perturbation to first order does satisfy, as an identity, that d mu equals 0. I take a first order perturbation in flat space, work out the Einstein tensor. You can actually check it from that equation. It is divergence free, just as an identity.
Covariant or partial?
Partial. Okay, because this is the correct expression to lowest order in H. You see, it should satisfy this one, but that involves a Christoffel connection, which would be first order in H. So it still must be that to lowest order in H, I only get this guy, and this is 0, just as an identity. That guarantees, by the Einstein equations, that this is conserved ordinarily as an identity. Okay, so this g mu nu 2 is some big messy thing called the Landau-Lifshitz gravitational wave stress energy, and it happens to be conserved. But it's not a tensor. It's called a pseudo-tensor. Okay, if you think about this g mu nu 2, I'm splitting g mu nu 0 and g up in this way is not covariant. Okay, by coordinate transformations, you can exchange the linear h for the second order h. The whole thing gets tangled up. So this is called the Landau-Lifshitz stress energy pseudo-tensor. But it is ordinarily conserved.
So my source term is g mu nu second order.
Yeah.
It's kind of simple.
Not in the pulsar system. Okay. What this is saying is that here's the pulsar. Now it has some t mu. When I go outside of the pulsar, I have those gravitational waves which came out. They contribute to the energy of the whole system. And that's the whole argument, is that you emit those gravitational waves, they carry some energy away. The total energy of the system is a combination of the energy in the t mu and the combination of the energy in the waves, which is this guy. The total stress energy, which is the right-hand side of this sort of pseudo-Einstein equation, right? I pull the nonlinear stuff over here. The left-hand side is conserved, so the right-hand side is conserved. So that means that the energy of the pulsar plus the energy of the gravitational waves is conserved. So the way you do the calculation is you work out h to first order, and then you go and compute this to second order. This is the energy flux represented by those waves. And then you argue that that energy plus the pulsar energy is conserved. So I've got some energy coming out. The pulsar must be losing energy. Okay, it's quite involved. But, all right, any other quick questions? Yeah.
Oh, maybe this is a bit off topic, but
by the way, feel free to leave if you want to have a break. Yeah.
if you're thinking experiments like LIGO, for example, is it known that, is there any possibility that it can discern detecting gravitational waves coming from the singularity or coming from this kind of pulsar, for example?
Yes, there is a possibility, but the problem with LIGO is that the wavelength, well, actually the only problem is that their sensitivity is not enough. Okay, so LIGO is only 1 kilometer long. Okay, so our h is a dimensionless number, right? And so basically what's going to happen is the length of LIGO will change as this gravitational wave comes through. The h values they can measure, I believe, are somewhere around 10 to the minus 19, 10 to the minus 20. Okay, so they can tell that this kilometer came kilometer times 1 plus or minus 10 to the minus 20, okay, with the LIGO detector. I may not have it. It's roughly that. Now, the question is, what gravitational waves could have come out of the Big Bang? You know, would they be 1 kilometer wavelength, or would they be much longer wavelengths? If they are much longer wavelengths, in fact, so inflation theory predicts there should be waves of all wavelengths, and the value of h should be approximately the same on all wavelengths. Okay, so they would say measure it anywhere, But it's easiest to measure it on the longest wavelengths, because basically the shift is larger. Okay, so the yeah, there's some other effects which I should also mention, which make it more difficult to measure on shorter wavelengths. The problem is the following: that in the expanding universe, the energy in a wave actually diminishes over time. Okay, so this is the redshifting of light. You know, if you've got a wavelength traveling in an expanding universe, as the universe expands, the wavelength gets longer, and the energy goes like the frequency, which goes like one over the wavelength, so that goes down. So light gets redshifted, gravitational waves get redshifted. So the problem is, if I've got these waves set up in the universe, and I go to shorter wavelengths, they will have been redshifted away more. Okay, so essentially if you like, they've gone through more periods of oscillation since the beginning of the universe, and they're redshifted away more. So these short wavelengths ones that LIGO could look for are weaker than the waves which BICEP is looking for. So BICEP is claiming to see H's of order 10 to the minus 6. So on these huge scales, on the whole sky, you look out at degrees on the sky, you're looking at wavelengths of hundreds of megaparsecs. Okay, huge gravitational wave. Okay, and that one, because it's oscillated less since the Big Bang, it actually is stronger. So its amplitude is about 10 to the minus 6. The H, just the dimensionless measure, is about 10 to the minus 6. That's what they're looking for. LIGO could go down to H of about 10 to the minus 20, but its trouble is those waves have a shorter wavelength, they've oscillated more, they've been stretched out more, and they've lost energy since the Big Bang. So the best hope for seeing waves from the Big Bang directly, as I said, BICEP is indirect, it uses this plasma effect. The best hope to see it directly is a proposed satellite called the Big Bang Observer. Okay? And the Big Bang Observer is projected to fly in 2025. It's still not confirmed. But that would be 3 satellites in space. I think they are separated by 100,000 kilometers. It forms a big triangle. And basically, they send laser beams back and forth on the arms of the triangle. They measure the length. And the claim of that design is that it would be able to see the gravitational waves predicted by inflation directly. Certainly if they're at the level seen by BICEP. Okay? So it's an expensive experiment. It's very, very difficult. But that's something to look ahead to in the next decade. But yeah, the great thing is that there are independent checks. I mean, there's many, many different ways to go after the same signal. No other questions? So is there a class this afternoon? So again, I will try to come. I know I usually fail, but I will try to come.